Alright, welcome to a new day. So we got a lot of cool topics to talk about. Before we get started with anything, I do want to just remind you that on the Zybooks website, it's a little hard to find which sections I'm asking you to do on each assignment. So go to that Assignments tab, go out to the Table of Contents. If you're inside of an assignment, go out to the Table of Contents, and then over here to this Assignments tab on the bottom right. And that will let you click on each assignment and show you all the points and then all the sections that are assigned and like what your current score is. Okay, so go there, and that's how you know. Also, only the Canvas due dates are correct. I had to make the due dates for Zybooks just the last day that I will let you turn anything in, so that it all transfers over. So like, don't pay attention to these. Only the Canvas due dates are correct. Okay, so with that, now let's get started. Let's talk first about errors. All right, I want to show you how you could speak C++ incorrectly, because I was taking care to speak C++ perfectly last time, and I didn't make any mistakes, but that never happens in real life. C++ will complain at you, the compiler will complain at you when things go wrong, and then also if things get past the compiler that are still wrong, oh man, still bad things can happen. All right, so let's talk about errors. So you got a few kinds, three main kinds, I would say. So you've got compile time errors, runtime errors, and logic errors, and I'll go through them in order. So a compile time error is probably the best one you could possibly get. That's when you have spoken C++ incorrectly, so incorrectly that G++, the compiler, has no clue how to translate your program. It won't even make machine code out of it. It's just going to show you an issue and complain and give up. So this is a good example of a compile time error. Instead of saying int x equals 42, you say int x equals 42, and the compiler's like, what are you even talking about, dude? So it'll give you an error, and it won't even make machine code. So let me show that to you. Let's make a new folder for today's lecture, and the way that you make a new folder after you've got in the right spot is you say make dir, mkdir. Dir stands for directory, which is just another name for folder. So I'm in my home folder. I would like to go into the code from class folder. Inside of that, there's a CSCI 40 online folder. And then inside of that, we need a folder for today. So let's do make dir lec02. So there it is, it exists. And I'll go inside of that, and that's where I'm going to work. All right, so that's my current working directory now. And so I'm going to open up two terminals so that I can show you the code and the compiler all at once. So let's make a new file called compiletime error.cpp. And it'll be just that one error. So int x equals 42. All right. So this won't even compile. If you try G++ compile time error, hit enter, it's just going to complain. It's like, all right, in function int main int. I have no clue what that is. Did you mean int? So it's very helpful. And it even shows you the line number. So line 5 is where the issue was. Did you mean int? And yes, I did. So that's perfect. And notice that it did not make any machine code. It did not make a runnable file because like you spoke C++ so wrong, it couldn't. So that's a compile time error. You're going to get those a lot. They happen. They happen to the best of us. And the next kind is a runtime error. So sometimes bad things happen as your program's running and they get past the compiler. So maybe the compiler isn't smart enough to know that an error will occur, or the error depends on like the way the program runs. So like something that the user gives you, for example. So a runtime error is when something bad happens as your program is running, and it's so bad that you can't recover from it. So a good example of that is division by 0. And I'll show you a program that compiles. It gets past the compiler, but still might divide by 0. All right. To show you the usefulness of runtime errors, or the unfortunate fact that they exist, I guess. Runtime error.cpp. And so here's a good example of a runtime error. So let's make a number, int x equals 42, correctly this time. And we'll ask the user for a number. Enter number, please, user, and we'll get it. We'll make space for a brand new number, call it n, and we'll get it from the user with cn. All right, so we have a number now, and here's what I'll do with that number. I will see out the result of dividing x by n. Do you see how this should compile? It is a good program, usually, right? It just depends on what the user gives me. So here, let's compile it, let's run it. I'll say G++ runtime error, and I don't want this to be called a.out, so I'll do a -o, and I'll have it be called just runtime error without an extension. And so now I have it. All right, so it worked, it compiled. I did not get any complaints from the compiler. It will run, and usually the program will run correctly. If I say 2 is my number n, then it will divide 42 by that 2 that I gave, and that's just 21. That's fine. So, okay. If I type 0, though, then this gets spat out to me. So that is not anything that I printed in my program, right? It's like floating point exception, core dumped. That sounds like a very bad thing. So that's a runtime error, all right? That's the program giving up, C++ giving up. I have no clue what to do right now. I cannot recover from this. So I'm just going to stop the program. That's what it does. That's a runtime error. You will get those too. And the final class of errors is probably the most subtle, and it's the worst. It's a logic error. So another word for logic error is bug. You probably heard that word before. It's just when you have an issue in your program and it runs, everything is fine. There's no runtime error, there's no compile time error, but just like the result that you get is not what it should have been. All right, but the program will run just fine. You're just going to get bad answers. All right, so a good example of a logic error, I don't really need to make a new file to show it to you, is just like, all right, let's make this variable int x equals 42, and then I'll make a variable called x plus 1 and shove inside of that the result of x plus 2. All right, so obviously this was named incorrectly, and if I use this anywhere and expect to see x plus 1 in that variable, I will just get the wrong answer for everything. I probably won't crash the program, but I'll just get the wrong answer everywhere. And those are super hard to track down. At least with runtime errors, it's like the program is stopped, and then you can try to figure out why. And then compile time errors tell you even the line that it's confused about. But logic errors, you get none of that. So those are the hardest. So those are the kinds of errors you could expect to see. They happen, every kind of them. You'll watch me make mistakes as the class goes on. All right. So before we go to other things that I want you to know, I just want to give you a demo of the kinds of things that we're going to learn in like the first half of this class, all right, the first like 8 weeks or something. So I would like to speak C++ to you fluently, all right, because it's just a language. Just pretend like it's a human language. I want you to pretend like you're a kid and you've never, like this is your native language, and I'm going to just speak it around you, all right? I'm going to speak C++, and I'm going to show you a bunch of things that you have not learned yet, and it will take a few weeks for us to get there, but I think you'll be able to understand some of it. All right, this is very useful. I took a Latin class in undergrad with a wonderful professor at Fresno State. Her name was Dr. Chapman. What she did for us was she just started reading from our textbook, just like fluently in Latin, and we couldn't understand because it was the first Latin class. But it really helped us get a feel for the language and like the pace and like how it works. So I'm going to do that for you in C++. Okay, so what we're going to do is we're going to model a counting machine, a counting device in C++. One of these things where you click it and the count goes up. So I'm going to make a brand new type, not int, not double. I'm going to make a type called counter. You can do that. All right. Again, I don't expect you to understand anything of what I'm doing on this slide. All right. This is a sneak peek. It's to get you ready so that you've heard these words once before. All right. So, all right, inside of every counter type thing, what should I have? What kind of information needs to be stored if I'm going to make one of these inside of code? Well, I'm going to need this number, right, that's on the window. So the data that better live inside of every counter should be the count that's on that window. That makes sense, I hope. And then what do I want to be able to do to this counting device? I want to be able to click this button, right, to increment that counter. Increment that counter's count and like scroll it down to like reset it or initialize it back to 0. So like what are the operations that I want to be able to do on this counter? I want to be able to like open it out of the box, initialize it. I'll call that init. Set the like wheel the thing back to 0 or something. I want to be able to press the button. I'll call that inc to increment the count on the counting device. And then I'll have I need a way to look at the counting device's window too. Like look at that number. I'll call that get count. Give me the count back that's inside of you, please. So, all right, we're going to make a new type that has those things. Let me show it to you. Again, don't worry if this is confusing. I have not taught you any of this yet. It's just I want you to hear these words once before I really teach them to you. But if you follow any of this, give yourself a pat on the back because this is where we're going. All right, so this is kind of what I want. Instead of like int x, I want to make a new type. I want to make a counter C or something. All right, and then I want to be able to tell it to do stuff like C, hey, initialize yourself. That's what that's going to look like. Hey, counter C, increment yourself like 3 times or something. So now the counter's count is 0, 1, 2, 3, right? And then I want to be able to get out the count that's inside that counter so that I can like look at it. I'll call that get count. All right, so that's the operation. That's me asking C ever so nicely for the count that's inside of it, and that's how I want to use my new type. All right. That's how you use it, right? That's how I want to use it. And now here's how you make that new type and tell it these things. So to make a new type in C++, it's called a class. And so it looks like this. And there are things that you want the user to be able to do. Those are public things. And there are things you want to hide from the user. Those are private things. I'm going to hide from the user the count that's inside that counter, but it needs it there. All right, so that's the count that lives within the counter. And the things that I want to be able to do publicly are all these things. Initialize the counter, increment it, and get count. So, all right, what do those things mean? So init, it is meant to be called on the line by itself, so it's a void function, essentially. It's a void operation. And what should it do? It should zero out that counter's count. It's like we're opening it out of the box. It's 0 now, all right? And then same with inc, right? When you call inc on your counter, you're just calling it on a line by itself, so we say void there. And what should it do? It should increment the count. So take the count, make it 1 more than it was, all right? And then get count, finally, is something that's not called on the line by itself. It is, you ask for it inside of a bigger place. So it's going to give back that int. Get count is its name, though. And there we go. So it should give back the count, and you return stuff when you give it back. So that's our brand new type counter. So here are the operations, and here's the data. And so when I run it, G++, counter.cpp, so compile first, call it counter, /counter. This is a very complicated program that prints the number 3 to the screen, isn't it? So that is my cool little demo of the day. Again, I don't expect you to have understood any of that, but hopefully a little bit of it made sense. Okay, I've said some words that I have not defined yet. That's okay. But this is where you're going, all right? You're going to be able to understand all of this code and even improve on it by the time we get to like week 8 or something in the class. So I hope that that was interesting to you. And now let's go back to your level. All right, let's go and talk about smaller things. Let's talk about variables some more. All right, so we learned about those last time. Let's go further. All right, let's go deeper. So a variable, what is that really? It's a box in memory essentially. To us programmers, it's something with some name, right, that can hold onto a value. So we can say, like my favorite example is int x equals 42. You got to give the type, right, and then give the name and give a value if you want to. So that's x, and it holds 42, right? Now I can say x all day long instead of 42, all right? So that's pretty nice. When you're making variables, you can't give them any name you want, all right? So variables can have the following name. So your variable names must start with a lowercase or uppercase letter or an underscore, so that your names of your variables must start like that. And then after that, you can use any of these characters. You can start using digits as well for your variable names. So that implies, right, that you cannot have a variable name that has a space in it. That is not allowed. All right, that's not allowed. And then also variables that start with numbers, that's also not allowed. All right, so like here are some examples of valid variable names, like underscore underscore hello is a valid variable name. ABC underscore 007, that's a valid variable name, but you can't start with a number, all right? And so because you can't use spaces, people have decided, well, how are we going to write multiple words inside of our variables? How do we delimit those words? So there's two schools of thought. People either like to capitalize the new words, so they call that camel case, so like they capitalize the new letters of brand new words so that you can kind of read it and have it make sense and it's not all jumbled together. So that looks like the humps on a camel's back, the capital letters. That's why it's called camel case. And then the other school of thought is let's just use underscores to separate the words. And so this is more of like the C++ style, and this is more of like the Python style, if you've heard of that language. But I'll use both in this class. So that's your naming conventions for variables. And this kind of line that like makes a variable and gives it a value, there's actually, that's a two-step process, right? You could have done less. I showed you that, right? You can just make the variable. That's called declaring it, all right? So to make a variable in memory, you declare it. You say its name and its type, and you put a semicolon. That's all you really needed, okay? So you do need its type, though. All right, so like int x semicolon, that is a declaration of a number called x, okay? So when you say this line, like it makes space in memory for something called x that could hold something later, but I mean the box exists. What happens? What does it hold right now? What do you think? What in the world should it hold? What is question mark? The answer is it holds complete garbage. All right? It holds a random number that you have no control over. It's just like whatever was in memory at that slot in memory right now It is completely random. You have no control over the values of your variables if you have not yet given them a value. All right, let me show that to you. Let me prove that to you. This actually might not work. It depends on how long my computer's been turned on, actually. But I will do my best. I'll run it on the server if I need to. Uninitialized. That is the right spelling, right? Uninitialized vars.cpp. So let me make a program that works like this. I'll be like int x, int y, and int z. So I've made 3 integers, and then let me print them all out. The more the better, actually, because it makes more memory and like you have a better chance of getting randomness. So let me compile and run this. And then perfect. Okay, so we're getting some random numbers in these variables, and if I rerun the program, they're new random numbers. Do you see that? So you have no control. Anything goes for these values. They could have been negative even. There is some pattern to them, actually. If you can kind of see, like, this is close to this one for some reason, and this is like either really big or really small, apparently. But again, that depends on the computer you're running this on. These could have been completely random numbers. Okay, so that's what happens. It holds complete garbage that you have no control over, and you should not bank on any value that an uninitialized variable holds. Okay, so with that in mind, you should always give them a value, and the word for that is initialize them. Give them an initial value. All right. Excuse me. So there's a couple ways you can do it. You could do it all in one fell swoop, like I showed you, like int x equals 42. That both declares x and then also gives it a value right away. Or you could do it in like a 2-step process. You could be like int x semicolon, and then it's garbage for a while until you need it, and then you say x equals 42. Okay? Excuse me, sorry, I'm losing my voice in the middle of the lecture. So, all right. Let's see here. So what happens with this is you say this, that declares it. It makes space. It's garbage right now. And then you come along later and you give it an actual value. So you don't have to say the type anymore once you've already made it. You just say x equals something. All right. So that makes it 42. So that gives it a value. All right. And I guess technically there's a third way you could have used cin if you count that way. Like make it, and it's garbage right now. And then before you really need it, like get it from the user and fill it, cin into the x variable. So that's like a third way to do it, right? But no matter what, before you end up using this variable or like printing it out, doing math with it, make sure it's initialized somehow. Otherwise, you're going to get really weird answers, and that's probably a logic error. Yeah? All right. So let's see. Is there something I want to show you right now? I think let's keep going. I got one more slide before we go to code. So this kind of thing, this kind of line where you're giving a value to a variable, that's called an assignment statement, all right? And that shoves something into your variable, and it replaces whatever was there. So I hate the fact that we're using equals for that, right? I think we should have used like an arrow instead, like a less than sign and a dash or something to mean an arrow. But this syntax is called an assignment statement. It's shoving whatever b results in into a variable called a. All right, so that's essentially what happens is there's a variable called a, and you're putting b into it, whatever b was. All right, it could be some big long math thing. So that's an assignment statement. That's what it does. Okay, and I don't like that. All right, so like if x was 42, and you say, let's see here, like x could have been whatever. Maybe it was garbage, and then you said x equals 42. You've just kind of changed what was there, right? So that's going to make it 42, right? When you say that, x equals 42. I don't like that because it changes things, right? In like the equality sign in mathematics means that like you've given a variable a value and it's never going to ever change, right? It's like you could come along later and say x equals 55 or something. That would change it. In C++, like that's weird, right? It's not equality anymore. Variables' values can totally change. There is no concept of like it's stuck like this right now. Actually, there is, but I'll show you that later, I guess. You can change normal variables, okay, usually. So that equals sign, I don't like it. It should have just been like an arrow, so that it's not It makes it clear that things can change, okay? So the way that assignment statements work is the right-hand side of it gets executed to a value first, all right? So the right-hand side of the equals statements, the assignment statement, gets executed, and we get some whatever value we need, all right? It makes a value that it can then shove into the variable on the left-hand side, okay? So that means, now this makes sense, right? This statement makes total sense now because you know what's going to happen. It's going to run this line, this side first to compute a value, right? X plus 1, whatever it is. Let's say that X is 42 right now. So that will compute 43, won't it? And then shove that answer that it computes back into that variable. So that will do this. It will change X from 42 to 43. Does that make sense? So you read it from right to left, and that's kind of disgusting. And I don't like that it's an inequality, but now you know, okay? So actually, people increment variables so much, like increment it by 1, instead of this syntax, people have made a shorthand for it, all right? Instead of x equals x plus 1, to just increment a variable, people have made this, all right? It's called x plus plus. So if you do x plus plus after your variable and put a semicolon, that's a very quick way to increment it by 1. These two are equivalent, okay? So actually now you know why it's called C++. You get the joke now, because like it was based on a language called C, and it's like one better than it, one more, okay? There's also a third way to, like a slightly more, less short than this, but shorter than this one, to increment a variable. You say x plus equals 1. And that's another way to increment a variable by 1. So plus equals does a plus and an assignment at once. And this is another way like to increment by other things though, like increment by 2. This one's only increment by 1. So you have options. And yeah, I think that is what I wanted to say there. So that's how you give values to variables. Once they exist, you just start using assignment statements. Okay. Let's see. So yeah, I think I have more to say. So let's talk about some new terms now. So there's quite a few of them, sadly. I said the word value a lot last time. What I mean by that, a value or a literal is another synonym for that, for value. It's a basic element of a type. So it's like the stuff inside of the cloud. All right. So like int values, for example, are the whole numbers that live within the int cloud. Those are like the final frontier, right, of integers. Those are your whole numbers, -4. Those are the basic values of the integer type, right? What I mean, the difference between value and non-value is the fact that C++ does not have to do any extra work to compute that thing, okay? So by extra work, I mean like doing math, like adding stuff together. For example, this is a valid assignment statement, int x, and a declaration all at once, right? Int x equals 2 plus 2, right? But that makes a box in memory, and it's not going to put 2 plus 2 in the box. It's going to compute a value from this. What is a value? It'll make 4. Does that make sense? It's going to get the final answer, essentially. That's what a value means. A final answer for whatever type you have. So the opposite of value is called an expression. All right. So this, for example, is an expression. It's a bigger thing. It takes some effort on C++'s part to compute a value. All right. It's going to do the work for you, though. So an expression is any combination of literals and operators. So like plus, minus, like this kind of thing for cout, for example. That's an operator. Okay. So a value, I guess technically, is also a special case of an expression, but I kind of differentiate the two, depending on if there's work to be done. So like this is a big long expression, and maybe it results in, it evaluates to the value 42 or something. All right. So those are some terms, and now you know them. Let's see here. Let's make sure I'm not missing anything. Yeah, I think now I'm ready for an example. All right, so let's go to division. Let's talk about division in C++. Multiplication was the star. You know that plus is the plus sign, minus is the minus sign. Division I showed you. Actually, didn't I? It's the slash. This one. That's divide. So division is the slash in C++. And I have a question for you. All right. I haven't shown you the answer, but like, what do you think is going to happen if I were to do this? Okay, so int x equals 5, and then I cout the result of x divided by 2. Technically, you don't need these parentheses, but I'm going to include them anyway for fun. It's like, what will be printed out to the screen right now? Am I tricking you right now? Is the answer D? See if you can figure it out. All right. So give me your best guess. I've not told you the answer, but what do you think should happen? All right. Obviously, 5 over 2 is 2.5, right? So let's see. Let's see if C++ agrees with us. So let's see. can I copy and paste this? Sometimes when you copy and paste from PowerPoint, it adds some weird characters, so we'll see. That seems to be happy, good. So, all right, G++ division dash O division. The answer is 2. Ooh, why is that happening? So A is actually the answer, and now you know why I made a separate section of the lecture on just division. All right, so this doesn't make any sense at all. What is going on? So what just happened is we ran into what's called integer division. All right, so remember ints and the int type, those are integers, right? What are the kinds of things that can live in the int type? 0, 1, 2, 3, -42, whole numbers only, right? Whole numbers only. So is 2.5 a whole number? Is it an integer? Absolutely not. So C++, well, if you're doing operations on integers, it thinks you want an integer back, all right? So integer division, so division, the division operator, the slash, in C++ works differently on ints rather than doubles. And you remember that doubles are the ones with decimal points. So there is no room in an int for the 0.5, right? For any decimal places at all. Ints can only be whole numbers. And so if you do integer division, and like the real answer was 2.5, C++ is like, well, you wanted an int, obviously, because you're doing integer division right now. I have no room for the 0.5, so I'm just going to chop it off, okay? So that's a little weird, right? So no rounding at all happens. It just chops off that decimal place. Even if it was 2.99, C++ considers that 2 if you do integer division and it results in 2.99. It'll make it 2, all right? And print 2, which is weird. So they just drop those decimal places, all right? So 5 over 2, as far as C++ is concerned, if we accidentally do integer division like we just did, it results in 2, okay? Which is disgusting, I know. But now you know, all right? And the way you can get what you want, the way you get the 0.5 is it depends on what the types are of the things on both sides of the slash. All right. So if we want double division, like actual division that gives me decimal places, it depends on the types that we give to this slash. All right. Double division depends on the types involved in the slash operation, not. So that's different than the type of the variable that you're going to assign the answer to sometimes as well. So like that is something to worry about. All right. So this is. Again, I've made a complete section of this lecture on just division because this is so weird, all right? So if you want double division, it depends on the types involved in the actual slash operation. And so what integer division means is that you give 2 ints on both sides of that slash. That's how C++ is like, all right, you must want integer division, then I will give you back an int after I do my division. So that's what this was. So x was an int, 2, just like this, right? It's not 2.0 or anything, just 2, that's an int as well. So this will do integer division because of that. It will result in an int and chop off the decimals. If you wanted double division with decimal places, one side of the slash, at least one side of the slash needs to be a double. Then it'll do it right. So like maybe the first side could have been the double. So if you did double, sorry, that doesn't look right yet. Double divided by an int, for example, that will be like, all right, one of those sides was a double. Obviously, you must want double division. You want decimals. So that will result in a double, for example. Another word for double is it's a floating point type, we say. That's something you'll read about in your book. It's like point means the decimal point, and like floating means it could be anywhere. It's secretly storing it in like scientific notation. That's kind of what that means. So if we want floating point division, that's another word for double division. We need to do this, either like double over int, or int divided by double, or double divided by double. That will give us the decimal places. All right, so we need at least one side of this slash to be a double. Okay, so let's make it happen. Let me also show you what I mean by it doesn't even matter about the variable type that's being assigned to. So like if I say this, double result equals x over 2, this is still going to give me 2 back. All right, still doing integer division, which is very confusing, I know. That's why I'm talking about this for a while. Watch. This is disgusting. It will compute, this will make 2, and it will technically make it 2.0, I guess. But this is int over int still. It will do integer division, even though it's going to put it in a variable that could hold decimals. Still 2. Disgusting, right? So, oh, sorry. Oh, no. Yeah, it's just that my editor is complaining. It's like, all right, it's giving me a warning, actually. It's like, you probably shouldn't be doing that. So if you wanted double division, here's one easy way. X over 2.0, right? Because now this side, that's totally double. It's got decimal places. So now it's int divided by double. That will give me double division or floating point division and do the right thing. There's my 2.5. Beautiful, all right? Sometimes you got two ints and there's no getting around that, all right? So like maybe you have int y equals 2 or something. And then you want to do like cout x divided by y. Obviously, that's int over int right now, yeah? You cannot change the type of a variable once you've made it. So there's no hope for us right now, it seems, right? I'm getting integer division no matter what. But what you can do is you can temporarily convert one of these guys to a double. It's not going to make it a double. You cannot change the type of a variable, but you can, like, for a split second, look at it as a double, all right? So if you have like an int variable that like one of those needs to be a double for just a split second, what you use is a disgusting thing called static underscore cast. All right, here's how you use it to make an int a double for a second. So you say static underscore cast, and then you put between angle brackets, less than and greater than signs, the type you want, double. That's what I want. And then between parentheses, you put the variable that you want to convert. So I'd like to make x a double, please. Static cast it into a double, we say. So that is just something you'll have to memorize right now. I'm sorry. One of the few things in the class you'll have to memorize for a little while until it makes sense. But that's how you make one of those sides a double. All right? So instead of this, we could say static underscore cast into a double, please, x. There. So now this side is, for a split second, it makes a double out of x. It makes 5.0, and then we'll divide it by the int y. And that will give me the 2.5 correctly. Okay? It's still, 5 is still stored as an int as x, though. This is just like, looks at it as a double for a second, gives it back as a double for a second. Okay? So, yeah, I think that's what I wanted to say about division. Now you know. The types are very important. The types around the slash. And sometimes you might want to print a double in a fancy way with like a certain number of decimal places. And the way you do that is with two things. You say fixed, and then you say set precision. All right. Set precision lives in a different header, a different library. It's called IO_manip for input-output manipulation. So let me show you that to you. So IOStream has fixed already. Set precision is another thing we need. It lives in this IO_manip library. Okay, so this one gives us set precision. And here's how you use it. Let's say that you've got an answer that you want to print with a certain number of decimal places. So let's print the next double with 3 decimal places of precision. So like we want 3 decimals after the decimal point, all right? Even if it doesn't really need them. So let's do this. You say cout, and then you start giving things. You give fixed and set precision to cout actually. So like I say this, cout, give it fixed. And what this is a special variable that does not get printed, but it controls how cout prints future things, if that makes sense. So I'm giving it fixed, which means always display the decimal point, please, with my doubles, and then I'll say set precision, and then give a number of decimals that I want of precision. I want 3 decimal places of precision. And this is, again, something I'm giving to cout. It's not going to get printed. It's going to control how future things get printed. Okay? And then now I give the thing I actually want to do. So like x over 2.0 or something. So that will result in 2.5, but I said I want it with 3 decimal places of precision. So here's what's going to happen. I get 2.500. All right? It'll also do rounding for you if it was like a longer number with more than 3 decimal places. So that's a very useful thing that you will need one day, and now you have it. All right, so hopefully you understand why I needed a separate section just for division. It's that complicated, but now you're good at it, right? So let's next talk about some other types that we know. We know about chars, right? Those are single characters, and strings are multiple characters. All right, so let's talk about those guys. First, I want to tell you, everything inside of a computer, you know, hopefully, is just a bunch of ones and zeros, right, at the end of the day. Everything's just a number, all right? Even characters. Characters in the char type, those are secretly just numbers, right? So what happened is back in the 60s, everybody got together, like some people got in a room and they're like, all right, let's decide on the encoding of characters. And that's called the ASCII coding, the ASCII table, all right? This is an acronym, American Standard for Communication something, information exchange. I don't know. We'll look at it in a second. But people decided the order of the characters and like which ones come first and what their numbers are. Okay, so like every time we try to print A to our screen, it's really giving a number to see out, and just like, all right, see out notices that we want to print it as a character though. It's like it's going to look up what that special number is and figure out what character to draw on the screen for us, essentially. So the moral of the story is like the capital letter A is the number 65 secretly. The letter B comes in order, surprisingly. That's just the number 66 secretly. The space character is the number 32. That's how it's been encoded in this ASCII table, right? That's just like what people decided. And I will prove that to you. First of all, let's look at it for a second. It's the American Standard Code for Information Interchange. There we go. So that's what ASCII stands for. And here's the table, all right? The first things, look at the decimal column over here. 0, 1, 2. These are all unprintable characters. But eventually you'll get to printable characters. It looks like there's space. It's 32. Is space. And then, where's new line? That's somewhere up here too. That's a printable character, right? I forget where it is. There it is. So it's the number 10. That's the new line character. It's encoded as that. Like 35 is the number sign. And then here are all, like, over here are the letters. Here's, like, A. A is the number 65, B is 66. They go in order, luckily. And then there's a gap with some symbols, and then it's lowercase. 97 is lowercase a, lowercase b is 98, then 99. Like, those are the orders of the characters in the ASCII table. Those are the numbers that are used to represent them secretly, okay? What's disgusting is the characters for digits, like the 0 character, is the number 48. The 1 character is the number 49. Those are not the numbers. They're the encoding of the characters, if that makes any sense at all. All right, let me prove that to you. So, chars.cpp. So, for example, when you print an A character to the screen, C++ understands that you want it to be printed as a character, even though this is secretly a number. It's secretly the number 65. But you can tell it to look at it as a number. You can be like, static cast it as an int, because we know it is a number. And then it'll print it as a number. So that's kind of cool. Let me show that to you. Static _ cast as an int, please, because I know that this is secretly a number. Print it as a number for me, please. Make an int out of it for a split second. Boop. And so there it is. It's really 65 secretly. Just C++ knows to print it as an actual character, though, when we ask for it that way. So that's a little weird. You can do cool stuff with that, surprisingly. Let me show you. So because these are just numbers, you can do math on chars, which is going to be very confusing, I know. So you can do the following. You'd be like, cout a plus 2. I think I need to static cast this, though. Static cast it as a char, even though you're going to do math. So what's this going to do? It's like, all right, this is 65. It's going to make 67, right? And then look at it as a character. Make 67 a character. That's the character C, and then print it as a character. You can do math on characters because they're just numbers at the end of the day. That is weird, but now you know. All right, so that's the encoding. Let's next talk about strings some more. All right, so strings are just a bunch of characters between double quotes, right? So let's talk about those. We can get at those individual characters. Is what I want to explain on this slide. All right, you can get at each individual character of a string, for example. And so, for example, if you made this string s equals hello with double quotes, really deep down in memory, this is what it looks like. There's your string s. It's got all those pieces. Here's the h is the first character. It's got all those individual characters that you can mess with. All right, and the way to get at them is you say s dot at, and then in between parentheses you put some variable name. Okay. Or sorry, not some variable name, some index, sorry. So that gives the index of the string that you want to look at, all right? So it goes to the ith index of your string s. indices of strings start at 0. In computer science, everything starts at 0, surprisingly. So if I want to get the character h out, I'll go to s at 0. All right, so s at 0. That will give back to me the h character. And you can also use this in an assignment statement to mess with stuff. That's pretty cool. Let me show that to you. Oops. All right, so if I want to make string variables, I need to include the string library. And let's make that hello. String s equals hello. And so obviously you can print out the whole darn thing. That's fine. That's using strings in the way we know already. G++. Let's compile and run. So I'll just print hello. But you can also get out the individual characters with the s.at operation. All right, and go to an index. Go to index 0. Go to index 1. Stuff like that. So I can say cout s at 0. S at 1. Oops, all right, let me get that to go away. There we go. That's what the code really looks like. And that'll print out individual things. There's the H, there's the E. I hope that makes sense. So those are the indices of those characters. You can also use the syntax as something to assign into. Think of it like a place that could be set, because it really is. You can go and change just the H character, just the E character, change the thing at that index to something else. So let's see here. Oh, I think, sorry, I was supposed to make it capital H. Capital hello, because I want to make it lowercase in just a second. So there it is, capital hello now. And now let's make it lowercase. Let's mess with it. Let's say s at 0, that character, whatever it was, change it, replace it with lowercase h now. And that's going to mess with the whole string, right? It's going to mess with index 0, and if you print out the whole string now, it's changed from capital hello to lowercase hello. Isn't that cool? So that's pretty neat. Let's see what else. What else do I want to talk about? I think that's where I want to stop for now. I will come back to this program and add more in just a second, though. Let's see here. I do have a question for you first, though. I think that's what I want to do. So here is a string, all right? I would like you to take a moment, pause the video, try this out yourself. Here's a string. It looks like this. It's been jumbled, right? It's just a bunch of weird characters. I'd like you to try to print out A, B, C, D in that order using just this string. Go into that string using the .at operation. Go into it at certain indices to get out A, B, C, and D in that order, okay? So that's what I want to see. So, as a hint, here's examples of those operations, okay? So yeah, try pausing the video, give this a try, and then I'll show you my answer. So like you got to figure out the indices of these characters so that you can print them out in the order that you want them. All right, did you figure it out? So what is this A character's index? Is it 2? It's the second character. It's not, right? It's 1 because it starts at 0. That's index 1, 2, 3, 4, 5, and 6. So I guess if you want to print out ABCD without like new lines, you just want to print it out in order. You don't want to add new lines after the end. So like you'll just say cout S2, because that's its name, right? S2 at, that's an ugly looking 2, sorry. There we go. S2 at 1. And then just a semicolon, because it'll just print that without breaking the line, because then you can do the same thing for index 6, right? That's the B. Then do the same for cout S2 at index 2, right? There's your C. And then D is index 0. You just do 4 lines of those things, right? And then you can break the line if you want to. So I think that's what I wanted to show you. Isn't that fun? I hope that makes sense and will be useful to you one day, I promise. So yeah, I just want to show you a little bit more about strings now. So when you use cin, right, it'll fill in a variable with what you type, and it depends on the type of that variable. So like cin into like an x variable, if it was an int, it will read numbers and put it into an int variable. If you read into a string with cin, you do have to be careful because it's only going to read one word, okay? So let me show that to you. There is a way to get like a full sentence with spaces involved, but by default, if you read in with cin into a string variable, let me make a variable, empty string, s2, ask the user to enter something, you're only getting a word at once. So cn read into S2. Let me print out the contents of S2 now. S2, then a new line. All right, so I'm making space for a string, asking the user to give me a string, and then it's printing it back. I'm only going to get a word, sadly. So if I type hi, I'm getting hi, of course. But if I type hi mom, I'm still only getting hi into S2. Okay, so cn on strings reading into a string typed variable is only going to get a single word out. All right. If you wanted everything, if you wanted an entire line's worth of stuff until the user types enter, then you use what's called the getLine function. All right. So here's how you use it. You make space for what you want to fill, like make a string variable again, and then on a line by itself, you call this thing. It's called getLine, and you ask it to do work for you. All right. So you say getLine parentheses cn comma line. All right. So that it's like get an entire line out of cn, out of the user's keyboard, and shove it into this line variable. That's like the two-step process. All right, so let me show that to you. I guess I should make maybe a new program, because this one's already got a bunch of stuff in it. So I'll call getLine.cbp. This lives in the string library. Also, we need string variables anyway. So here we go. Now we can ask the user to enter a line. And string line is what we say. We make space for it, and then we say getLine from the user's keyboard cn into the line variable. All right, so this will mess with the line variable. It will put stuff in it for us. So this gets an entire line from the user, including all the white space up to the enter. But it actually doesn't get the enter at the end, though. All right, but it gets all the spaces in between. And then here, let's just spit it back out after they type it. So we'll say cout, you typed, and then the line, and it gets everything up until you type enter. So it doesn't actually get the enter. So we still have to break the line. And so enter line, hi mom, 1, 2, 3, 4 exclamation points. And so we get the whole darn thing in that line variable, and these all have indices now, right? You can get to any of them. I hope that makes sense. Let's get line. That's very useful. And then I think the last thing I want to show you is just a little combination of all this stuff we've been learning so far. So let us capitalize a lowercase string. All right, so let's get a lowercase word from the user. We'll ask them nicely for one, and then let's pretend that like it's a proper noun or something, and we have to capitalize it. All right, whatever they give us, we have to capitalize it. No matter what they give us, though. So like if they give us hello, the string hello, we have to make it capital hello, capital H. But if they give us ABCD, we can't just like hard code make it a capital H at index 0, because if they gave us ABCD, we have to make capital ABCD. See that? So it depends on what's there, what we capitalize. So we have to be a little tricky about it. All right, we have to be careful. We have to work for any lowercase character of the alphabet. We have to be able to capitalize it properly. We are always messing with the 0th index, right? Because that's always their first character, is always going to go at index 0. Index 0, index 0. But what needs to be replaced, what it needs to be replaced with, depends on the original character. See that? So the answer is going to lie in the ASCII table. All right, so if you stare at this thing for a while, look it up on Wikipedia too, it's a prettier table. If you stare at this table for a while, if they gave us an A, right? A was 65. Or sorry, if they gave us a lowercase a, excuse me, because they're giving us lowercase words. If they gave us lowercase a, that's 97. And we want to make it capital A, right? That is 65. If they give us a lowercase b, that's 98. We want to make it capital, we need to turn it into 66. You see that there's a bit of a pattern here? Because these go in order, there is a pattern. Here's like the number line of the characters in the ASCII table. Here's capital A, here's capital B, and then over here after those, like after the whole alphabet's over, starts the lowercase characters, right? Lowercase a, lowercase b. What we need to do, if we get a lowercase a, we need to like shift it on down to be capital A, right? We need to move it from here to here. It's a bigger number, we need to make it a smaller number, right? Go to there, please. If it was b, lowercase b, we need to also shift it on down, right? Go to capital B. Do you see how this distance is the same for both of those characters? That's the beauty of this. So 97 to 65, that's 32 away, right? Same with B, 98 to 66, that's still 32 away. It's always 32 away. Whatever that distance is, you can hard code it as 32 now that we know that. But even if you didn't know that, it's just like whatever this is a bigger number, this is a smaller number. What's the difference between them? Well, they are in fact, what are they? They are in fact characters, so you can be like this. You can be like that. Isn't that crazy? That's pretty cool, right? It's that's your distance. These are both numbers secretly, so you can do subtraction on characters. That's the offset that we need to go to. And that's what we want to replace with. All right, so that will turn into a program now. Let's make a brand new program called, I guess, capitalize. Capitalize.cbp. And so I want to mess with strings, so I'll get a string library up in here. And what next? So let's ask the user for, it's a lowercase word we want from them, right? Enter a lowercase word. And so because we're just getting a word, I can use a cn, right? Just by itself into a string variable. That will get just one word. So now it lives in the word variable. And our job now is, right, to change s at 0, or word at 0, excuse me. Change word at 0. We want to take whatever that character was and subtract this offset from it, right? That offset, that distance is, we can store that as an integer. What's the distance between the capitals and the lowercase characters? Yeah. That's just the distance between any two of those characters, right? That's our offset amount. We know it's going to be 32, but even if you didn't know that, you had some other encoding, this will still work, all right? Because they go in order. And so that's what we do. That's what we need to do now. So word at 0, whatever you are, your ASCII code is going to change, right? You have a big number right now. We need to make you smaller down to here by subtracting this distance. And it's going to work for any lowercase character, all right? Your character, if you're A or you were H or anything in between, all the way to Z, take what you were and subtract that distance. So take your ASCII code and subtract that 32 that we're calculating from here from it. Does that make sense? That's the secret. All right, so please yell at me if this is making not enough sense, as it should. Come to office hours. Ask me on Discord. I'm happy to help. But that is a cool program that we can understand. All right, so let's compile and run it. Enter lowercase word, hello, becomes capital hello. I've messed with it. I've subtracted the right amount in the ASCII land, ASCII encoding land, and it's working. And then ABCD, still ABCD. Capitals now. All right, so it works. No matter what that first character is, we figured out the secrets, and we know how to make it capital. I think that's really cool, and I hope you do too. And that is where I want to stop for the day. All right, so there's plenty more to talk about. We will get there in due time, but that is enough for the lecture at least. So I will see you in the next video.